All right, for this screen, we're going to use my Lancer that I absolutely love. And if you go to austinmeyer.com, there is a section on this airplane where you can see all the build logs, all the pictures of this thing under construction, which is kind of fun. We will do the props 1, and there's nothing like a propeller. They're so much more efficient than jets. Up until you get to about Mach 0.6. That's how fast you have to go for jet speed better. This thing has one prop. It's a constant speed. So there's all the different kinds, right? You can do manual pitch if you adjust the pitch manually. Constant speed means the pitch adjusts itself to hold a given prop RPM, which most props are. Main rotor and tail rotor for helicopters, of course. A VTOL cyclic, that's a vertical takeoff and landing, so it actually has collective and cyclic on it. A constant tip Mach. So this is something that Jay Carter of Cartercopter taught me. If you set the RPM of your propeller to hold a certain tip Mach number as a function of power, that's like just an awesome RPM, a really efficient RPM to hold. And so this is an experiment I don't actually see deployed very much, but if you were to say, well, at half power, I want to hold a tip Mach number on the propeller of 0.4, and at full power, I want to hold a tip Mach number of 0.6, you're going to be very, very close to your maximum efficiency. And then this one I thought of myself, constant average angle of attack. My theory is you want to hold a constant angle of attack on average across the entire propeller plate that's very close to maybe 2 or 3 degrees, maybe 0 at the tip. And so this option will cause the propeller to automatically open or close its pitch a bit to hold a constant angle of attack. And then you got the lift fan, say of an F-35, which will absorb power from the jet engine to drive a fan. So these are the various different types. For my evolution, it's constant speed. Adjust the propeller pitch to hold a constant RPM. For blades, turning clockwise as seen from behind, looking forwards. Prop clutched, if you want to have the prop able to be clutched away from the engine, and you would apply a little button in the 2D instrument panel, and there's probably a command as well to engage and disengage clutch. Prop ducted, that's if you have a big duct, like an inlet or a nacelle around the prop. And what these ducts do for propellers is they keep the tip losses minimized, because the propeller is now spinning inside a duct, you see. And the tip losses don't really happen so much because the air can't make it around the prop because the duct is there stopping that from happening. And so a duct is good for super, super low speed because it blocks those tip losses. That's not to be confused with an engine nacelle on a jet engine, which slows the air down and actually makes the propeller or the compressor more efficient at high speed, because the inlet does some of the compression first before the compressor has to. Hotel brake. That is a little brake you can put on some airplanes to stop the prop from turning, even though the engine is still turning, which you can get on a free turbine. And then you can use your engine as an auxiliary power unit without the prop turning. Prop radius is obvious. Root and tip chord. Well, that's the root and tip chord, or leading edge to trailing edge distance on the prop root and the prop tip. Ellipse fraction. What? All right. So so we have an object file. You know what I think we should do? I think we need to get into an airplane that does not have an object file, so we can actually see what's really going on with the propeller. Okay, so my little file open dialog is not showing up in my little grabbing video thingy, but now you can see this. Okay, so here we go. This is a little eVTOL I made, and why don't we take a look at the props on this thing, because the props are very visible. And since I don't have an object file for this airplane, you'll actually see the geometry of the airplane, and you can see each little blade or each little element on the blade, right? As we use blade element theory, you can see each element on the blade. Isn't that cool? So let's go back to engine specs props, which is what we're doing. And so the ellipse fraction, that is how close the propeller is to an ellipse. You see, I just set it to 1, and now we get like an ellipse shape on the prop. Or if we go to 0, then it's not an ellipse at all. It's just a straight taper. And so it's just, fine-tuning the shape of the prop. And the ellipse shape does get you closer to a minimum of induced drag, because an ellipse planform is a planform that gives a minimum induced drag. And of course, the Supermarine Spitfire fighter from World War II exemplifies that with its wing. Mach limit right now is 1. And if I drag this back, what you should see is, there we go, the simulator starts to sweep the prop back so that it does not exceed, in this case, only 0.2. This is a very, very, very slow turning prop. And since I asked for it to only sweep back as necessary to hold less than Mach 0.2, I'm a little surprised we're not sweeping the tips a little more first. But the simulator will automatically sweep these props back to try and hold a minimum tip Mach number. Yeah, so if I had more RPM and speed, we would see this tip kind of, we would see the tips sweep back a little sooner. Oh, here we go. Now we're starting to see it. If I set it to about 0.27, you can see the tips are sweeping back to try and hold a Mach number. Normally we just enter 1 if there's no prop tip sweep at all. Tip, fine, and coarse pitch. So, of course, propellers, they can open up to a coarse pitch or go down to a fine pitch, and so you can enter what those limits are here. And I measure these out at the tip. Propeller manufacturers often measure this at like the 70% span or the 75% span. I'm not going to try and get into what percentage span because that can be different from one propeller manufacturer to another, so I just say at the tip. All right, and this is interesting. Design true airspeed at prop disc and design propeller RPM. What does that mean? Well, what this means is, with the design true airspeed at prop disc of 140 knots and a design RPM of 600 RPM, here's what that means. Imagine this airplane is going forward at 140 knots and turning 600 RPM on the prop. And this is a very, very, very slow turning prop. That's why that prop tip Mach thing was kind of hesitant to sweep the tips back. The twist of the prop is perfectly set so that the propeller completely just screws through the air like a bit through balsa wood on a drill, screws smoothly through the air at 600 rotations per minute, advancing at 140 knots. This is the twist of the prop blade. And that's going to be a zero angle of attack across the blade. So you will have zero angle of attack across the blade if you're going forward at 140 knots at 600 RPM in a perfect world. Now, the actual air getting accelerated through the disc and whatnot is going to cause some differences in there. But this is like your theoretical 600 RPM going through the air at 140 knots. Now, what you might decide is, hey, I want some more lift at the root. So you might pump that up to 4, and you might even say, I want the tip to wash out to 0 or even negative angle of attack to minimize my tip losses. And so maybe you do that as a -2. And so that's going to give you a little more angle of attack at the root and less at the tip, which might be more efficient because you want that lift centered in near the center of the prop if you can, not out near the edge. Because if it's out near the tip, then of course that pressure wants to leak around the tip, and there's your tip vortex, and there's your inefficiency. AOA root to tip span-wise power. So this would be, let's say you want 4 degrees at the root and 0 at the tip. You would enter, let's see, enter 2 to treat as, yeah, there you go. So if you enter 2, what this is going to do, and you can hold the mouse over anything to get a tool tip on your own time without watching this video. But this entering a non-linear power here like 2, that's going to hold that 4 degrees, out a good bit on the prop and only kind of bring it down to 0 right near the tip. So it might be a good idea to enter a positive power here to kind of hold that angle of attack for as much of the prop as you can, including out kind of near the tip where you've got your airspeed from the prop rotating, and then boop, just go down to 0 near the tip. Max allowable prop pitch. Well, that's how much pitch the prop is allowed to have, just due to its twist, because you don't always twist a prop up to 90 degrees, right? So that's just the maximum allowable pitch each element is allowed to have. Now, with this entered, what's kind of cool is we can go here, and there's only one of these because they're all the same, right? All 4 props in this airplane are the same, so you only need to show it once. We've got the rib, leading edge, and trailing edge offset. You can enter some values here to kind of, reshape. Here, let's come up with something we can see. Yeah, there you see, look at this, what I'm doing here. Okay, wow, that's awful. So you can basically reshape the leading edge and trailing edges of the props if you want a little bit, just to get the prop to look exactly like you want. And wow, am I managing to mess this up? Oh yeah, this also needs to go to 0. There we go. Okay, now we're fixed. All right, so I don't want any offsets here, but you can get those if you want. And then it shows you the rib chord. It shows you each element incidence, shows you each element sweep, each element mean aerodynamic chord, angle of attack, and Mach number. at some given test speed. So, for example, if I enter a test prop speed of 600 RPM and 140 knots, the angle of attack, it's negative 44.7 all the way across. But if the prop opens up, as it will, by 44.7 degrees, using the prop controller, you'll clearly see 0 degrees angle of attack all the way across the prop. Because all those numbers are the same. The prop just has to open up 44.7 degrees to get that 0 degrees angle of attack across the prop. And we know we'll get 0 degrees angle of attack across the prop at 140 knots and 600 RPM because, of course, that is exactly what we entered here. 140 knots and 600 RPM is just a constant angle of attack across the blade. And then what we've got is just some information. Some people like the prop advance. J equals V over ND, and that's 2.95. Some people want a rotor advance. J equals V over omega R, that's 0.94. And then some people want a prop advance in inches per revolution. They call that in the inches, and it's 283.5. So in other words, these labels here, these are just the different ways propeller manufacturers or propeller selecting people look at prop labels to find what kind of prop they want. And so we have those little specs there. So the bottom line here really is you enter the speed of the airplane and the RPM of the prop that you want to optimize for, and then you can hop over here and check out what your various advance ratios are, and then test some different speeds and RPMs to see what kind of angle of attack you're going to get across the prop. So that is the props 1 and 2 tabs.